So we've take a look at this traceroute application to give you a feeling about what is this round trip delay, or what will be the kind of a common the round trip time for our TCP connections. Usually it's within the 100 millisecond range, and for most of your gamers, you're probably expecting the ping or the lags within 100 millisecond range. Well, the next metric we're going to talk about is throughput. Throughput is defined as the rate at which bits transferred between sender and receivers. Throughput sometimes have different names. Sometimes refer this as link transmission rate, link capacity, bandwidth, depends on which context you are talking about this throughput. But overall, this is a rate for the amount of data you're going to transmit over a period of time. And because this is a rate, we kind of have two different metrics, or two different of contexts when talking about throughput. The first one is this instantaneous. This is at a given point of time, what will be the throughput. The second context for throughput will be an average. This is the rates averaged over a longer period of time. We probably have seen a mixture of both of them. For instantaneous throughput, this is like you open up your download application and you can see what is your current download speed for this particular task. And for the average throughput, this is like, so after you download, your file has finished downloading, you see a reading or some values for how long it takes, what will be your average speed, download speed. So throughputs are kind of in this similar flavor when it comes to how to measure the rate for the transmission. One thing to note is that this transmission range or the transmission speed over the network is being determined by the slowest link. Well, recall that we talked about internet is really this store and forward network. So before you send the package to the next hop over your network, you need to make sure the whole package has been received. And through that link, that's the kind of like the, well, I forgot how you, maybe this is not the proper way to say this, but it's like you have a bucket, you want to hold them water, and the capacity of the bucket is determined by the shorted piece, right? Making that bucket, assuming that you have a wood bucket. Similar scenario here, because the transmission link has many hops, the slowest hop or the smallest link capacity will be the dominating factor that's limiting your speed. Well, so here is kind of further explains what would happen when it comes to the average throughput be determined by multiple hops. So considering here another kind of theoretical scenario, let's assume we have two hops between server and our end system, and there are two links connected with one router, and they have different link capacity or throughput. One is this smaller one, RS. The other is RC. In either of the scenarios, so in the first case, RS smaller than RC, and in the second case, RS is greater than RC. Both of this average end-to-end throughput are determined by the smaller or the smaller value or the slower link. And you can imagine this kind of a intuitive when it comes to what will be the effect on the throughput. And oftentimes for those links with lower capacity, lower slow throughput, we're oftentimes referring them as the bottleneck link. Well, bottleneck link, just to kind of rephrase here, is a link on end-to-end path that constrains end-to-end throughput. your shortest piece in your wooden bucket. Well, so what would happen in the internet? So what would be the limiting factor when you're connecting through the internet? Oftentimes, the bottleneck happens at the network edge. So that is how you access the network. The edge comes two parts. The users of the end system are considered as the edge, or RC, C for clients here. And at the other end of the network, the server may also have a limiting throughput, RS here. In practice, usually the bottlenecks is not happening at the core in the network because they generally have higher capacity, more availability, although they are being shared. But they are the larger pipe, if you will. And in comparison, the access network is usually where the bottlenecks come from. Well, one interesting to note is that when we talk about throughput, we're usually measured it in terms of bits per second. Well, in the context of networking, the units we're using is usually in terms of bits. And this is different from what you might see when you're trying to download a file. The downloading speed is usually measured in terms of byte. Bit and byte. In here, as we show here, this link capacity is in terms of R bits per second. But in your download, when we talk about downloading speed, it's usually in terms of byte. And in abbreviation, they usually have lowercase for bits, uppercase for bytes. And they may not write it this way, so Mbps will be the similar metrics that's being used. Well, this kind of a nuance when it's come to describing the network. And you probably, you might have purchased a network with 200 megabits per second or 100 megabits per second, and we're looking at your download speed. The download speed usually being represented in terms of bytes. So that is 8 times. So 8-bit is a byte. So theoretically, the network speed that you purchased divided by 8 should be the maximum download speed that you can expect from your network. However, because this is a theoretical value, and also given the store and forward and their various components in the network, you probably won't really even reach that maximum speed. Well, speaking about nuance in network, in addition to this unit, I'm not sure if you guys noticed, well, you might have noticed before, when it's come to the unit for storage, it's also a problem. Well, maybe problem is a harsh word. It's not consistent, let's put it this way. So when it's come to storage, we are usually measure them in terms of megabytes, right? So 8 bits is 1 byte. But when you're trying to purchase some hard drive or memory, well, memory not the case, especially for your solid state drives or your hard disks, they are oftentimes measured, or jump drives actually, they are oftentimes measured with megabytes in the decimal units rather than the binary units. Yes, is there a question?
I haven't started it.
Okay, well, I guess it's kind of not that intuitive what I'm trying to explain here. Let's try. Right, there you go. So if you're looking at this chart here, for storage units, there are the so-called megabytes in terms of decimal versus the megabytes in terms of binary. as engineers, binary makes more sense, right? Because this is how our data are being stored in terms of byte. But probably to make this value looks larger, the manufacturers for the jump drives, for the SSDs, they oftentimes using this decimal megabytes, and they both mark them in terms of gigabytes. So you can compare that. If you consider 1024 as 1000 or 1K, then this 1 gigabits doesn't have much of difference. But as you can see, as the number increase, the difference becomes more and more significant. So when you have 1 terabytes, the difference between the decimal representation and the binary representation is significant. Okay, well, speaking about the units, well, we're still using imperial units versus metric units. I think your physics and math teacher can tell you which one is better. Well, anyway, so let's come back to our network discussions. Well, our next topic here is really about protocol layers and their service model. This is kind of a concept on how we structured the computer network. It's also an important one. It will guide our discussion in the following chapters. Because the protocols or the communication network has many components, so we really want to have a better structure to describe different parts. And this abstraction will help us to kind of break down a complex system and solving different parts of it and make them work collectively. Well, we're dealing a complex system. So we want to have this explicit structure that allows us to identify the relationship of their different components. This is kind of first reason for why do we have a reference model for this layer structure. Secondly, this layer structure helps us to modelization or give us the capability to switch and swap pieces of the system to reduce the complexity when it's come to updates and maintenance. And this is like where Keeps implements a new protocol at a certain layer, such that the under layer and the layer above it can still function properly. So overall, for this layered structure in our network, each layer will provide a service that is performing certain actions within that layer. And then for each of these layers, they will use this service, they will utilize the service that's being provided to them directly below that model. Maybe I should show this slides to give you a better understanding on what are the relationship between different layers. So for each of the layers, there are a total of 5 of them. For each of the layers, they will performing certain actions of that layer so that we can swap in and swap out different protocols to support that layer's functionality. And at the same time, each of these layers also relies on the layer below them to provide service. And from their perspective, they're just only looking at a API or interface without really worrying about what are the underlying mechanism to support those services. And each of this layer of the protocol can be a mixture of both software, hardware, or a combination of both of them. And you probably can see this. on the top layers like application and transport layer, the majority of the tasks are handled by software. And whereas as you go down this layer structure, at physical layers and linked layers, the majority of functionalities are actually performed directly by the hardware, like sending and receiving signals. And also another important feature about our layer structure on the internet is that although we kind of show you this as a stack, each layer of the protocols is actually being implemented in a distributed fashion. That is, when it comes to the applications, you might have the same protocol running on multiple end systems. And at the same time, there's might be not one, but several end systems to collectively perform certain tasks, and that form the same system. So inherently, the Internet Protocol stacks is a distributed system among different end users. Well, there's also some criticism when it comes to this layer structure for protocol stacks. For example, sometimes we don't really have a clear cut between different levels. Oftentimes, certain functions might be performed by one or two layer together, rather than have a clear cut on this is for this layer, the other is this, the other function is for the other layer. Sometimes I look at this Internet Protocol stacks and think about programming paradigms. Well, from your experience, you've probably seen this. Object-oriented programming seems to be the default design pattern for when it's come to do the programming these days. However, you probably have seen many programming languages that are poking holes in this nice structured object-oriented design pattern. So by providing like pointers, like reference, well, this kind of breaking up the structure of a design pattern also happens in our internet protocol stack. This is maybe one layer may have duplicated functions from other layers, which kind of reduce the efficiency. Okay, we kind of talks about overview with each of the layers. Now let's look at each of them individually and talk about maybe some examples for them. From top to bottom, on the first layer, on the top layer, it's actually the fifth layer, is the application layer. The application layer supports network applications that you are pretty familiar with, such as HTTP, which is the protocol for web application. SMTP is a protocol for early email systems. FTP is another protocol for early file transfer applications. So for our application layer, this is where the network application and their application protocols reside. Well, the next layer is the transport layer, which talks about process-to-process data transfer. And in this transport layer, there are two famous applications in internet. They are TCP and UDP. TCP is the transmission control protocol. UDP is the user datagram protocol. So both of them are providing process-to-process transfer. Well, coming down this protocol stack, in the third layer, we have networking, where the network layer, its function is to, network layer is responsible for moving network layer package from one host to another. And in here, for the internet's case, the most famous protocol is the IP protocol, the internet protocol. And there's also a various routing protocols that supports how each of the end system can find one another. Well, coming down this protocol stack, next we have the link layer. Link layer provides service to move package from one node to the next. And well, in here, we have our Wi-Fi protocols. This is the IEEE 802.11. And for the wired connection, Ethernet is the dominant link layer protocol. And finally, we have our physical layer. This is something we're not going to really cover in this textbook. It talks about how the hardwares perform the communication between each of the links. Well, so here, now we have it, the 5 layers structure for internet. Again, this is a conceptual model. Between each of the layers, in between them, from the upper layers perspective, the lower layers are transparent. Transparent temporarily meant they don't worry about how this information are being delivered, and they trust the lower layer will provide the service. And from the upper layers perspective, the lower layers functionality is just a function call or in hardware interface that it can extract data directly without varying the underlying details. Well, this 5-layer structure is really important, and you should kind of memorize this. When talking about this, I want to draw attention to some nuance when it's come to what are the protocol layers functionalities resides, or where are they resides, or what are their functions. Firstly, from the application layer, the very top, is talk about supporting network applications. So you can think this as one process or one application that is running on your computer. And each of the application might have multiple threads or multiple process, well, as you learn from the operating system case. And for each of those threads or process that needs data communication over the network, it will have an instance for the transport layer. So that is, the transport layer will provide the process-to-process data transfer. Again, coming back to the operating system's perspective, in operating system, we're interested in how can we do the process-to-process communication. Right? Each of them have their own region in the memory, and they should not interfere and should not have access from one to another. And the operating system supports how each of the process can change data between them. And similarly, here in our internet perspective, the transport layer protocols are responsible for handling process-to-process communication. And this is done through the TCP and UDP sockets. And then coming down to the next layer, the network layer. So from the network layer's perspective, they're interested in routing datagram, which right now you can think this as a package, from the source to the destination. It just implies that this is a source end system to the destination end system. So the job for the network layer is not to specify which process data belongs to which application. But rather, the network layer protocols is responsible for delivering the data from your computer to the server. It's only interested in routing this data from a source hosts to the destination hosts. And coming next, for the link layer protocols, well, link layer protocols talks about this one hop communication between your end system to the next immediate router, or the router to the next immediate following router. So this really just talks about this one link between two entities. They can either be end systems or routers. And here, they're responsible for data transfer for their neighboring elements. Now, Wi-Fi, Ethernet, each of them have their own features and parameters. Right. So in here, from this layer structure, this is really how we designed the internet with this different components, and we have these components work collectively, and oftentimes work in a distributed fashion to provide service. Well, this 5-layered protocol stack is not the only conceptual model that has been proposed, but it's the default one. Some of you might have heard this ISO OSI model. So this is another protocol layer model that has been proposed. Right now, in my opinion, we're kind of inclined to stick with the internet protocol stack structure rather than having the OSI models. But it's still worth mentioning what are the major differences between these two models. Very quickly, if you're looking at this layer structure, in our OSI model, it has 2 more layers that's being added between the application and the transport layer. Application talks about what is the what the application does or what they do, and the transport layer is responsible for providing this process-to-process communication. And between them, in the OSI model, 2 layers has been added. One is this presentation model, presentation layer. And presentation layer is to allow applications to interpret meanings of the data, such as having encryption, compression. Sometimes you might want to have some data descriptions, so that data description, the metadata, are kind of helpful when it's come to interpreting some of the functions in the application. Well, and obviously, it's probably beneficial to have some compression, decompression, encryption, security mechanism being added before the applications. So that was what being proposed to adding a presentation layer in this protocol stack. The second layer that has been added is this session layer. Session layer talks about provide this synchronizations for data exchange, and also, as the name session implied, they want to build a checkpoint and recovery mechanism. So session is like, for web applications specifically, different users might want to have, you might want to track the behavior of each of your user. And information that you use to track their behavior oftentimes be referred to as a session. It's like you are having a session with that user, and that user have certain values there. Checkpoint, recovery, synchronization, those are some kind of common functions for the server and to one specific user. And you might want to have multiple checkpoints for different user. You might have different synchronization mechanism for different user. And that's why this session is being kind of proposed. But again, I guess one of the reasons the OSI model wasn't being largely adopted is because not all the web applications requires presentation session functionalities. So here, we're just mentioning OSI model for kind of ordering mentions when our discussions in the network stacks. All right. Well, we talked about these protocol layers. Here is an illustration on how these protocol stacks are being utilized into transmitting the package between different entities. So here we're assuming a simple case here. We have a client known as the source and the server known as destination. And each of them are implementing this 5-layer of internet protocol stack. And in between them, this is the network of networks. We're assuming here we only have one switch and one router, but you can easily expand this to multiple hubs. So here, we're showing one switch and one router. An interesting observation here is that for switch and routers, they do not have all these 5 layers of the internet protocol stack. This is really because their functionalities for switch and routers are only focused on the last 3 layers. And in the switch cases, it's only a function on the last 2 layers. So what type of, how much of the protocol layers are being implemented is a major difference between switches and routers. In fact, when we talk to network layer and link layers later in this text, in this class, we're going to look closer on what are the functions for switch and what are the functions for routers. Well, just for now, I just want to give you this impression that when it comes to functionalities, switches and routers implement different layers of functions. And apparently router, because it's implementing one more layer, the network layer protocol stacks, is more powerful, or has more functions when it's compared to switch. So after identifying the components in our network, we need to define some terminologies. For each layer in our internet protocol stack, when we're referring to the package that being the packet that's being sent over the network, we tend to use different terminologies when describing them. When packet is being exchanged at the application layer, we refer them as message. So this can be some data you want to send from the source to the destination. And as we're passing this message down the network stack, recall that, so this message is needed for the same application running on both the source and destination. And when we push this to the transport layer's responsibility is to identify which thread or which process does it need to be used. So to maintain this process-to-process communication, additional information need to be added to the original message. And we refer to this as a header for the transport layer. And after adding this header at the original message, the packet we're going to send between transport layer protocols is being referred to as a segment. Well, then we're going to push down this message to the network layer. Network layer is responsible for finding this host-to-host communication. And this includes finding the routes, and also how to identify themselves. So at the network layer, we need to add additional information to the message that's been passed from application transport layer. And to do that, we're adding another header, this network header, HN here. And we're referring to this network layer packet as datagram. Well, again, network layer is responsible for finding the route between the source and destination, and also how to identify the end system, using IP protocol. Well, then this message will keep being pushed down the layer structure to the link layer. So link layer is only responsible for this one hop, the neighboring hop communication. But still, to identify who are their neighbor and maybe doing some error detections, you still need additional information. And that is adding one more header or a few more fields on top of the original message. And we are here referring this as HL, so this header for the link layer protocol. And this in expanded message, or the expanded packet is being referred to as the frame. So for the packets being sent in each of the link layer protocols, we refer them as frames. And finally, after being processed with the link layer, it will be pushed into the physical layer, which is responsible for the sending the bits. And that is not something we're going to discuss extensively. So we're just going to assume that the physical link will just send it out to the next network element. If you missed the animation here, so once the link layer frame has been pushed to the physical layer, it will be sent into its neighboring links. And when the next elements in the network receive that data, well, in our case, the switch receive the data, it will go backwards from the network protocol stack. And in switch's case, it only implements physical layer protocols and link layer protocol. So it will kind of take out the physical layer message and examine the link layer frame and act accordingly. And by examining that link layer frame, the switch will forward the message to the next hop. And in our example, the next hop is a router, and it's going back to the same process. Firstly, the message or the packet will be picked up by the physical layer protocol and then push it to the link layer, which will examine the header for the link layer, and then further being pushed into the network layer, which will examine the network layer header to do the network layer functionality. And then as each of this header file has been used or examined, new header files will be created for according to the functionality or according to the routing needs of this network. And you are seeing that in each of the links, we're going up to the stack for processing the package, and then we're going down the stacks for preparing the message. And eventually, this will be the reverse process when the message reaches the destination. So in here, when the package has been received at the destination, each of the layers will kind of examine their respective headers. And finally, this message will be delivered to the application. Well, there are many underlying details in this process, and this is actually what we're going to study in later chapters. Well, the title for this textbook is Computer Networking, and the subtitle says a top-down approach. And by top-down, this is really meant we're going to describe our internet in terms of going top-down through their protocol stacks. So in chapter 2, we're going to start off with application layer. Then in chapter 3, it's transport layer, followed by network layer, and so on and so forth. Okay, just a quick recap. I know I kind of talked a lot of information here. An important component for this slide is that you have a kind of impression on what is the protocol layer structure, and be mindful on this different terminologies that we're going to use when describing the packets that's being used in each layer of the protocol. And we probably will coming back to these slides from time to time so that we can have a better understanding on what is happening in our discussion in this class. Okay, so in the rest of this chapter, we have a short introduction on network security. I feel like this will be an interesting reading assignment. We've talked about a lot of, we have talked a lot of things that's not directly related to computer networking. But here, in this section, I find this is kind of easy to follow. I will assign this as a reading task for you guys to go through this section in this chapter. However, I want to point out, or after reading all those, I want to leave you with one observation from the network security perspective. That is, what are the internet was originally being designed? So in here, at the beginning of internet, we're expecting a group of mutually trusting users that are attached to a transparent network. Well, put it differently, we're assuming that the computer network are all trusting friends that's trying to do something exciting and useful. And we're trying to have the network as simple, as straightforward as possible, such that it's transparent to different users. Well, and very quickly we learned that there's no trusting users over the network. Engineers are kind of naive when it comes to mutual beneficial projects. Well, in this chapter, we're kind of talks about some common terminologies about virus, worms, sparewares. Well, in the early days in the network, I consider those are the utopia time of computer networking, Arcadia, if you will. But we learned this very well. There's many malicious entities out there. So be careful when you're surfing the internet because you never know what would happen to you. All right. There's also a short history kind of about the computer network. This is another component of the chapter I'm going to skip. My feeling is that I wouldn't call this history of the network because computer networking is still very young. It's probably just a little bit over its 30s. Right? We're seeing the first actual network starts in the early 1980s. So it's just a little bit over 30 years old. I wouldn't even call it history. I believe the other day I was having a conversation with an anthropology professor. I asked him, so for how long of a item or artifact you will consider it as an item with historical value? I think he told me it need to be 30 or I think it's needs to be 30 years or older. So from that respect, I wouldn't really call computer network has a history because it's so short. But still, there are giant figures, interesting stories about them. So if you have time, you are interested, maybe just kind of take a look in this chapter. All right, so that's kind of concludes our discussion in chapter 1. Any questions? Okay, so chapter 1 is more, well, it's an overview. So we didn't really touch upon a lot of the technical details or protocol designs or algorithms. From chapter 2, we're getting serious about computer network, and we're going to touch upon some of the technical details. Okay, let's get started. So we just look at the layer structure, and the top layer of our 5-layer internet protocol stack is the application layer. Oh, here's a quick question. So what is the terminology to describe the package that's being transmitted over the application layer. Does anyone still remember?
Is that the message?
That's right. Very good. We're starting with message, and transfer layer, we refer to them as segment. Network layer, we refer to the packets as datagram, and for link layer, they are frames. Well, I'm going to repeat myself a few times such that you guys will eventually remember them. Okay.
Professor,
So,
before we continue, I have a
yes.
question regarding the homework. Do we
Sure.
need a book for the homework?
Do you need what?
Do we need the book for the homework?
Not necessarily. And you can use a older version of the textbook as well. So for
The older versions of the textbook are the same as the new ones?
The older versions also works for answering the homeworks. If you're looking at the homework assignments, I have the detailed description about the problem rather than referring to question numbers. So you don't have to have a textbook for your homeworks.
Okay, thank you.
All right, so chapter 2. So in this chapter 2, we're going to talk about the conceptual and implementations of our network applications. This is the part that's many of you have been, many components of this application layer you're familiar with. But here we're going to provide you with an overview and also look into some details. Well, in this chapter, after talking about the principles of the network, we're going to use 3 examples as the application layer protocol. The first one and the obvious choice will be the HTTP protocol, which is a protocol for our web applications. The second one will be email protocols. And here we're using the email from their early days, SMTP, POP3, IMAP. You probably have seen them if you're manually configuring your smartphone for emails. They're relatively legacy protocols, but they're still being supported for backward compatibility reasons. So nowadays, the Gmail, Outlook, or SharePoint, they have more advanced functionalities for emails, but still, the 3 email protocols we're mentioning here are a good starting point. And finally, the third application layer protocol we're going to describe is DNS, the domain name service, which you probably know as well. It's the protocol that translates the URL to the IP address. Okay, so in addition to talk about this 3 different protocols, we're going to talk about network application architectures. Specifically, there are 2 dominant ones. One is this client-server model. The other is the peer-to-peer model. So we're going to briefly touch upon the P2P model as well. An interesting feature or a large components for application layer protocols is that well, this will be a good opportunity for you to practice some networking programming using the application layer protocols. In the textbook, they have a socket API, which essentially is the interface between the application layer and the transport layer. Well, if you have time, if you're interested, you can follow through them. Maybe when we're coming back next Monday, I can also talk about or kind of show you a little bit on programming for building a HTTP server and client server using using Python. But there's more when it comes to the application components that we might touch upon later in this chapter. Okay, so we're going to talk about application layer protocols. This is the protocol that's reside at the end system for each of the components. So in here, we're interested in what will be the application running on the end system and the servers. And for the rest of the network, we're just going to view them as a service that's simply supporting all the data transmissions. There's really no need for the programmers to write a software that's looking at how messages are being transmitted from one entity to another. This, again, is a service. So let me kind of rephrase myself a little bit. From a network application architecture's perspective, the application developer can only choose what kind of can only choose what kind of architecture for its application, rather than have a control for the network. That is, the network architecture is fixed, and it will only provide a specific set of services to the application. And when it comes to the application architecture, the programmer can make a decision on whether they want to have this server client-server model or peer-to-peer model. There are, generally speaking, two structures for application. So programmers at this point don't need to worry about the network. They only need to worry about how the end systems work with each other. So for client-server architecture, server is this always-on hosts, which will provide information and response to requests by the client. But in our web application example, the web server that resides either somewhere in the server room or at some server that's providing the web server application. And for users or for the clients, this is the web browser that you open up to access the internet, to access the web application. Also, in this client-server model, the clients do not communicate directly with each other, but rather than go through a server. And to identify the server, each of the server will have a generally fixed IP address. And because it's a stable fixed IP address, so the client will be able to connect to them. And also, server nowadays is rarely a one single server machine, but rather achieved by certain virtualization. This can be a virtual machine being shared in a server farm, or in some cases, this can be a collection of servers that providing the same or running on the web server. Well, the second type of application architecture will be the peer-to-peer, sometimes written as P2P here. Compared to the client-server architecture, P2P really don't have a dedicated server, but everybody in the system serves as both the client and the server at the same time. An interesting feature about our P2P structure is that it has a better scalability, because when there's more participants in the network, there's more user and more server at the same time. I think I have a slide to kind of illustrate this. Oh, yes, illustrates in more details. So when it comes to network application architecture, the client-server model is that each of the users will be connecting to a server. In this example here, we're assuming that the server is in an institutional network. But of course, each of the end systems or each of the hosts can be a server themselves. So for example, you might set up a local server to host your own web application, or you might have, well, I'm not sure if they are still popular these days, but there were storage devices that you can add into your own network for storing movies, pictures. And those can be viewed as a server by themselves that is providing data within your local network. When it comes to server, they're always on has a semi-permanent, largely fixed IP address that will not change over time. And to support more user, this might be through a virtualization, or you have a data center of machines that's running on the same application. From the client side, the client don't have a fixed IP. They can have a dynamic IPs, and they actually acquire one when they comes online. A major functionality for the routers is to manage this dynamic IP and also support how to find the permanent IPs for other services. Also in this model, an important note is that the clients don't really talk to each other, or for most of the cases. This is when it's come to your gaming applications, although you are fighting other players, but the message are not directly communicate between you and the other user, but rather through an intermediate server for relay the message. All right, so the other network application architecture is peer-to-peer. So in here, everybody serves as both the user and the client. Well, the advantage is this self-scalability that we mentioned, but it also have drawbacks, especially when it's come to a stable connection. You probably have the experience yourself. We're using some peer-to-peer applications such as BitTorrents, this uTorrents, right? The Pirate Bay. Many of those applications you might have experienced. If you're looking at the old torrent file, it might take forever for it to download because there's no resource available. Plus, although the P2P structure largely relies on each of the participants to provide both the server, both the functionality and making requests, sometimes they still need some centralized information to facilitate their forming their structure. So that makes the system relatively hard to manage. Well, talking about the network applications, we really need to talk about how the application communicates with one another. And from our operating systems background, we know that the applications might have multiple processes, and each of the process might have some lightweight process known as threads. And the inter-process communication is supported by the operating system. And in our case, when it comes to computer network, you also need to have inter-process communication that is supported by the network, by the network themselves. Well, to further explain or further line up our terminology here, we defined what do we mean by a client process and a server process. Bear in mind, one application might have multiple processes, both for server and the client. But in computer network, we're more interested, or we're focusing on just talking about one process. So the process that initiates the communication is defined as the client. So we're targeting at process rather than application here. And the process that's wait to be connected is the server. So client initiates requests, and server is the kind of responder of the requests. When it comes to the P2P architecture, both the client and server reside, both the client process and the server process resides on the same hosts. And so our focus when it comes to application layer protocols is to how can this process being supported for client process and the server process. And in this application layer protocol, oftentimes we're referring to this process communication by sockets. There's also this idea of sockets programming, which essentially talks about what are the interface between the application process to the rest of the network protocol stack. So in this illustration, you can see that here is our 5-layer network protocol, and the sockets is this interface between the application layer and transport layer. So notice here we're interested in application, although it might have multiple processes, we want to focus on discussion on this supporting one process for that application. And this one process application is known as the sockets. And you might have seen this socket programming before. The name sockets, I guess, come from the power sockets. They have this plug in and use, or plug in and play type of behavior from this. And when it's come to the socket programming, this is really the application send and receive data through the sockets without worrying about how the underlying protocol stacks will carry out this. And socket programming will be the interface that's being supported by the operating system as well as the networking components. Well, so then the next questions about this interface for process communication would be, how can we identify processes between one hosts to another? So each of the hosts might have multiple applications. Each of the applications might have multiple processes. How can we make this distinction? How can we distinguish one to another? Well, then this bears the question of how do we address each of the processes? Well, we address each of the process by 2 identifiers. The first one is a IP address, which has a total of 32 bits. In IP version 6, this is 64 bits. Right now, you can think this as just a series of numbers to identify each of the hosts. So that is, computers are being identified. In fact, it's the network interface is being identified by IP addresses. Well, but that is not enough. For IP address, we can only identify hosts. And for the specific application, well, in this application, we're referring to this one process for that application. That needs to be identified by a so-called port number. The port number are 16 bits. Well, and you can kind of count 2 to the power of 16 is the number of possible port numbers. 2 to the power of 16 is about 60,000 or so available values. And when it comes to the port numbers, the first 1024 are reserved. And we're going to talk more about the port number IP address later. So in here, I'm hoping to line up three concepts here. Firstly, the majority of the applications is being implemented in terms of client and server architecture. And for identify each of the applications in the client and server, we're identify them in terms of process. And the process is the same concept that we've seen from the operating system. There will be client process and server process. And then to do this process communication, the library or the interface we're using at the application layer is being called or being referred to as the sockets, which essentially is a library. But because they are this is a kind of a historical term. So for this API or this interface between applications, it has a special name called sockets. And then along this way, to identify or to do the socket programming, you need to identify the hosts as well as the process. And to do that, we have two things. Use IP address to identify hosts and use port numbers to identify the process. And here there are some examples for popular IP address and port numbers. So some of the popular IP address is like 192.168.0.1. Does it sound familiar? Oftentimes this is a reserved local area networks router address. So 192.168.0.1. Sometimes it's .0.0. So you get the idea for this. And for the port numbers, some popular ones like port 80 is for HTTP, 25 is for web server, and there are many more. So for the port number below the 1000, you only have a reserved function for certain type of applications. Okay, so after talking about the principles of this network layer application, let's talk about what are the exact functions for this type of, or this layer, the protocols in this layer. Well, a application layer protocol defines how an application's process running on different end systems, of course, pass message to each other. And in particular, the application layer protocols define the following items. Firstly, it will define the type of message exchanged. Examples are what are the request message and what are the response message. And the second type of information will be provided here is the syntax of the various message types. Now this is where are the fields, what are the possible values, a set of parameters, if you will. And the syntax need to be consistent so that each of the application can run on them at the same time. Together with the message syntax, there's also semantics. The meaning for each of the field also need to be tabulated or explained. And finally, this might be some rules for determining when and how a process will send message, and also the sending and receiving mechanism, some rules in between them. So again, overall, the application layer protocol really defines how applications process will pass message between each other. And there will be syntax, there will be rules, those type of information. Well, for application layer protocols, although they don't need to worry about how the message are being passed to them, they still have all this need to be designed field. So to standardize application layer protocols, there are a few different organizations and entities, and we have seen this in different flavors. Well, if you recall RFC, this is an organization that's kind of discuss and make rules on how to define protocols. And there's many RFCs to define protocols such as HTTP, SMTP. So in those RFCs, they are describing the type of message, the syntax, the rules. But for each different implementation, or for the programmers, they can still have some flexibilities in terms of how to implement the syntax and message. That is where we've seen kind of different versions of the browsers or different versions of web servers. Although all of them running on the same protocol, the implementation behind them will be different. So the RFCs only define the format and the rules. The implementation is up to the programmers. Well, in addition to some of those common, well-known protocols, there's also proprietary protocols. Those are some of the protocols defined by the companies running on their own application, and they don't want others to interfere or be part of there. So Skype is the example used in the textbook. There's also a lot of proprietary protocols for video streaming. Amazon, YouTube, they all have their own type of video streaming services to provide application layer services. Well, before we finish up today's lecture, there's one more thing I need to mention about transport layer service, which is the layer below our application layer. So that is, if you're looking at previously, the application layer protocol defines the message type and message syntax. And through our sockets, we pass this message into the transport layer, which has each of the package being wrapped around as a segment. And the segments will go through the process to ensure data integrity, throughput, timing, and security. And those are some discussions that we're going to continue when we return next time. All right, well, that's all for today's lecture. Any questions?